Transfer function is a very basic thing which will be used extensively throughout the subject, but there are actually two ways in which we can represent a transfer function. One is time constant form, where the factors are represented in the form of s tau plus 1, where tau is referred as time constant. The time constant of a system is the time required for the system's response to reach 63.2% of its final steady state value after a sudden change is applied on the system. I hope it is not the first time you are hearing the word time constant. The concept of time constant actually originates from the electrical circuits where we have resistance, capacitor and inductor, and the expression of time constant is derived in terms of resistor, capacitor and inductor. However, that is not required here. If you carefully examine the definition, then you will find there is a limitation for the systems to have a time constant. Actually, the time constant is not defined for a system whose final value cannot be determined, like a linearly increasing function or exponentially growing function or even a periodic function. The advantage we have in time constant form is that we need not to calculate the DC gain as it is already present in the transfer function. The another form of the transfer function is frequency constant form, which we generally use as we can easily find the value of poles and zeros, which we have already seen earlier. Let's quickly move to our main topic, which is dominant pole concept. The dominant pole concept refers to identifying the poles that most significantly influence the dynamic behavior of a system, particularly its transient response. This concept is used to approximate higher order systems into lower order systems, still retaining the essential system dynamics. Dominant poles are the poles of a system's transfer function that lie closest to the imaginary axis in the S-plane. The poles must have negative real values, whereas there are no limitations on the imaginary values of the poles. However, the dominant pole concept cannot be applied if even a single pole exists with the real part having positive value in the transfer function. In other words, in the S-plane, there should not be any pole which is lying on the right hand side of the imaginary axis of the S-plane. The negative poles represents exponentially decaying function, whereas poles with positive real values represents exponentially growing response. If a pole is positive, then the system will grow exponentially rather than decaying, causing the system to be unstable, and as such, we cannot apply the dominant pole concept in these situations. Suppose there are two poles in the transfer function of the system P1 and P2, and if the magnitude of the pole P2 is equal to or greater than 5 times the magnitude of the pole P1, then P1 will be called as significant pole, whereas P2 will be referred as insignificant pole, which can be removed from the transfer function. Now, let's try to understand this with examples. This is the first example where the transfer function is equal to 1 divided by s plus 2 into s plus 16. Here, 16 is the insignificant pole as it is greater than 5 times of 2, which is the significant pole. Therefore, we can remove s plus 16 from the transfer function. Let's see another example where we have 3 poles and we are having 2 significant poles and 1 insignificant pole. Here also s plus 16 is insignificant pole and we can remove this term from this transfer function. Here, as you can see, we are having a positive real value of the pole. Therefore, dominant pole concept cannot be applied in this transfer function. Now let's consider the case when we are having complex roots. The term s square plus s plus 1 is having complex roots, which we can easily find by using the formula for finding the roots of the quadratic equation. When an quadratic equation is in the form of ax square plus bx plus c, then the value of x will be equal to minus v plus minus under root of b square minus 4ac divided by 2a. Mathematics is a prerequisite for every subject of every branch. So, mathematics should be the first subject which students should cover before moving to other subjects. Anyways, let's come to this question. If there are complex roots, then you should always keep in mind we have to compare only the real part of the pole. We will not compare the imaginary part of the pole. Therefore, here in this example, we can see 8 is greater than 5 times of 1 by 2. Therefore, 8 is the insignificant pole and the other two roots, which are complex roots, are significant poles, so that we can remove s plus 8 term from this transfer function. But the question is, can you just remove the insignificant pole and the remaining transfer function will be the approximated transfer function? The answer of this question actually depends upon the representation form of the transfer function, and this is the place where students usually commit mistakes. Let's take an example and see how we are actually supposed to remove an insignificant pole from the transfer function. We know that we are having two ways of representing the transfer function. One is time constant form and the other is frequency constant form. I have taken an example. If you observe carefully, then you will realize that the transfer function in both the cases is actually representing the same system. First, let us consider how we are supposed to remove an insignificant pole from the time constant form. This is actually quite simple. You can simply remove the insignificant pole and write the remaining terms as the approximated transfer function. But in frequency constant form, the procedure is little bit lengthier. The formula for approximated transfer function is equal to partial DC gain divided by significant pole or poles. Partial DC gain is the DC gain which we get by hiding the significant poles and afterwards calculating the DC gain as usual. Like in the considered example, we know s plus 2 is a factor which consists of the significant pole. So first we remove this term and then find the DC gain of the resulting transfer function, which will come out to be equal to 1 by 4. Now putting the value of partial DC gain in the above expression, we can find the approximate transfer function to be equal to 1 by 4 divided by s plus 2. Irrespective of how you proceed the question, you must be getting the same answer in both the cases. In frequency constant form, it is little bit lengthy and students also commit silly mistakes here, as they also consider the significant pole while finding the partial DC gain. That's why it is the only concept in the whole subject where it is actually beneficial to use time constant form for finding the approximated transfer function. Other than this concept, we majorly use frequency constant form. But still, you should be aware of both the procedures.